It's an example that you have seen already yesterday, but I just want to mention that I typed over the keyboard the word hello in the I spell twice to correct it, which is to find what is a word in the dictionary which is the most similar to the word that I typed. That is, that means that the fewest number of typing mistakes takes me from a word in the dictionary to a word that I typed. I typed hello misspelled. How many errors, typing mistakes happens between hello and cat? I think that it's about 7. That will be the edit distance, because I probably have to delete all the word of hello and insert all the word of cat, so it's actually 8. Between hello and hey, the distance is a bit smaller. I have fewer number of spelling mistakes, which is about 4, because some letters are common, but I need to replace the Y by a whole part of LLWO. And on the other hand, if what I typed, is the word hello with W, and there is a word in the dictionary that is almost the same, the distance is only 1, then we are saying the distance between these two words is quite small comparing to the distance to these two words. So fewer type of mistakes happen, so it's more likely. The probability that that's what I meant to type. If this is what I actually typed, the probability that this is a sequence of events that happens, that's what I meant to type, that is what I actually typed. This probability is higher than the probability that that's what I wanted to type, and this is what I typed, which is in terms smaller than the probability that this is what I had in mind and this is what I typed. If I just say every typing mistake has the same probability. Make sense? Just ask how many mistakes should happen to explain I wanted to type the word hello, but I typed the word hello with W. One more spelling mistake, I type W by mistake. Edit distance will tell me there is one mistake that happens where mistake, now we are counting as either I inserted the letter that shouldn't be there, I didn't insert a letter that should be there, or replaced one letter by another. Each one we are counting as what. That's why edit distance is so useful. So we are measuring the distance between what I typed, which was hello with W, to each word on the dictionary. Practically, of course, we can do much less than this work, but theoretically, we can check the distance between what I typed and every word in the dictionary, find what is the most similar word, and autocorrection will replace the hello with the W with the correctly spelled hello. Making sense? People on Zoom? Same. And so this is when they explain where every spelling mistake happens independently of other spelling mistakes. You essentially say every error has a probability that it occurs, and now I need to ask what is the chance that this happened, and also this happened, and also this happened. Let's think about the case that I wrote hello, but with an A over there. Then there are 2 spelling mistakes, and what is the probability that both spelling mistakes happen? Of course, in this case, the edit distance is not 1, but is not 1, but it's 2 over here. 2 spelling mistakes happen. It's still the closest out of the 3 words that I mentioned, the closest in distance of edit distance. But why do I think about it as a sequence of events that took me from that's what I wanted to type, that's what I actually typed, HALLOW. Well, one spelling mistake was replace A by an E, one spelling mistake was introducing the extra W that shouldn't be there. What now? Can I just say that the probability that these two spelling mistakes is just a sum of the probability? Not really. I cannot say that the sum is a sum, but I can say that edit distance is summing up penalties. Again, edit distance summing up penalties. So if what is the probability that this happens and also this happens? It's multiplication of probabilities. This event happened and independently this event happened. What the chances they both happen? The multiplication of the probability. Among the three of you, anybody knows how do we move from a product of probabilities to sum of probabilities, or to sum it all? Common trick that is maybe the first trick in machine learning. How do I express product of probabilities? People on Zoom as well. How do I move from edit distance wants to sum up different values? If I think about a sequence of events that takes me from this to this sequence of errors that happens each one independently, I need to ask what the probability that this happens times what the probability that this happens. This will tell me the probability that they both happen if they are independent. How do I move from one to the other? I just need one word as an answer. You might have heard this word, definitely have heard it in any machine learning course. The penalties that we'll give to the edit distance, chance for zoom, the penalties that we'll actually give to the edit distance will not be one, but maybe some spelling mistakes are more likely than other. Switching between A and E, especially for me, not English as second language, very likely that this mistake happens. Maybe other probabilities that other mistakes happens, but I still want to ask what is the penalty of the distance if I want to express it as to use product of events. I will use log likelihood. Well, you are not taking the probability itself, but you're taking the log of the probability. And then when you're summing up logs of values is like the log of the product of these values. So in particular, the most likely event, the one with the highest probability, will also give you the highest log. So the closest distance. Everybody understand why I think about edit distance as really a distance between one string to another string, and when I typed something or said something to a speech recognition or specified some gesture to my Android device when I'm Scrabble to type something, when it asks what is the most likely thing that I meant to type, if that's this gesture that I just gave. And that's how it all works, despite errors that you have. Speech recognition, image recognition, all over the place, edit distance. But edit distance usually assumes that errors happen independently. If you want to assume that this mistake makes another mistake more likely or less likely, if it happens after that, then you need to look for Viterbi algorithm. Viterbi algorithm. Not entirely sure about the spelling. Can you check it out? It's a famous guy that explains how we can find the most similar signal, even if typing an A and after, let's say, if I typed an A I meant to type an A, and instead I typed AS. Why? Because A and S are next to each other on the keyboard, and maybe I typed both of them one after the other. How do I spell Viterbi?
At the end is I.
I. Yeah. Not in this course, but a very, very central algorithm. Okay, yesterday we started to talk about similarity between polygonal curves Yesterday we started to ask about similarities between polygonal curves. We have one polygon, P polygonal path. Sorry, I'm only talking about polygonal path here for a second. Polygonal path, meaning it has a vertex P1, small P1, P2 is the next vertex, P3 is the next vertex, and as you all know, the assumption is that between P2 and P3 there is a straight line segment that is connecting them from P3 to P4, there is a straight line segment, and so on. And this set of vertices describe a polygonal path. Maybe it's trajectory. It's a GPS location of a car that I measured, or location of an ant that I measured by taking a video capture of the ant as it moves. A bird that had a tracker. Although maybe it has time, maybe it doesn't have time. Right now I'll assume it doesn't have time, just have every vertex have an XY coordinate. Here is another polygonal curve, and I want to ask what is the distance between these two polygonal curves, capital P and capital Q. Again, why do I care about measuring signatures? Because I want to ask if I wrote a loan in this way and I deposit in the bank this signature. Is this similar to this, or is this more similar to a different signature that happens to be in the bank, and maybe somebody's trying to fake my signature, something like this. What is a curve that is most similar? What is a signal in music or in speech that is most similar? Dynamic time, some of these problems have better algorithms since, but the algorithm that I described had a lot of usage in this context, and a lot of usage in particular in geographic information system, in GIS, geographic information systems. They have a lot of usage. I'm going to show you in navigation, in trying to say, GPS usually has some errors associated with it. It was your GPS actually want to find what is a route that exactly you were moving into despite the GPS errors and locations. And and we are going to see two algorithms for measuring similarity between polygonal paths. I want to say that the distance from this to this is 5, and the distance from this to this is 5, this is 30. So this polygonal path is more similar to this polygonal path between these libraries of polygonal path. This query path is more similar to this thing in the library comparing to the distance to this one. The distance between this and this should be larger. Now, when I'm talking about the similarity, I also want to find a matching, an assignment between the paths. I want to say that the similarity is that probably this point of the A points to this point of the A, this point to this point, this point to this point, etc., to see what matches between them and also what's the difference between them, which points don't match. And this matching doesn't have to be one-to-one. If we think about GPS location, that the curves are GPS locations, then I was once driving across this road, and here are the location of my GPS when I was driving across this road. And the next day I was driving along the very same road, but my GPS records a location, every 10 seconds, which means that if I'm driving slower, lower velocity across the same road, and remember GPS locations are not always in the same place, then it doesn't mean that every vertex here has just next to it another vertex in the other part, and they don't necessarily have the same number of vertices, right? On the black curve, I was driving much faster than I was driving along the red curve. The red curve has many more sample points around. I still want to say it's the same road probably. Cool, movie time. So as I said, we are going to see two algorithms that are closely related to each other. One is a dynamic time warping. Dynamic time warping, which will abbreviate dynamic time warping, and one will be the Frechet algorithm. So two algorithms very similar to each other. Old video, but I like it, so you have to.
Finding a Curve in a Map by Alon Efrat, Lingeshwaran Palaniappan and Carola Wenk from University of Arizona, and by Helmut Alt and Günter Rothe from Free University of Berlin. Let alpha and beta be two curves in the plane. A well-suited distance measure for curves is the Frechet distance, which is defined via continuous and monotone reparameterizations of the two curves. The definition can be visualized as follows. Consider the two curves, one blue and one green in this example. Now imagine a man walking on the blue curve and a dog walking on the green curve. Of course, the man holds the dog at a leash, which is the black line segment here.
Who let the dogs out?
Both the man and the dog can control their speeds independently, but are not allowed to move backwards. Then the Frechet distance is the length of the shortest possible leash with which the man and the dog can walk their curves from beginning to end.
Let's hold for a moment. So the man, the person nowadays, the person was walking on the blue, dog walking along the green. That's the two curves that I want to measure the distance between them. I want to find the alignment, which point, which to which one. They are only moving forward. They cannot move backward. However, one can move faster than the other. Why do I allow them different speed? Because I want to get the freedom that if once, if I may want to say this, the same trajectory or not, then as a person moves along the black curve, then the dog might have to move occasionally faster or occasionally slower. Remember, this curve, we are introducing all these methods because there is noise in the data, so we want to find is there a good matching or not despite all this noise. So the dog, everybody notices the dog's wiggling its tail. The dog will move in some speed along it. The Frechet distance will be what is the length of the leash, the length of the leash that is sufficient for me to do the whole trip while using a leash of this length. That is, sometimes the dog will be small if the leash is 1 meter, sometimes it will be less than 1 meter closer, but never more than 1 meter. I'm looking for the maximum. So the distance would be find out of all this possible schedule, who is moving faster, who is moving slower, out of all the possible schedule, what is the minimum length of the leash that I can do the whole trip and the man will never lose the dog. We'll get back to it if you missed me so far. But all in all, the point is to find the matching between these two curves.
Which is defined via continuous and monotone reparametrizations of the two curves.
In the video it
The
continues.
definition can be visualized as follows. Consider the two curves, one blue and one green in this example. Now imagine a man walking on the blue curve and a dog walking on the green curve. Of course, the man holds the dog
Sorry,
in a
there
leash,
is
which is the black
an
line
obvious
segment here.
problem. I will post the link, but yes, let me also place it in a better way. Okay, see, I think that you see it now. Yeah.
Let the dogs out!
Both the man and the dog can control their speeds independently, but are not allowed to move backwards. Then the fauché distance is the length of the shortest possible leash with which the man and the dog can walk their curves from beginning to end. Now consider the following scenario. Eric goes on a hike in the mountains and he records his coordinates during the hike with his GPS receiver. The sequence of Eric's GPS positions describes a polygonal path, and we would like to identify the hiking trails on which he traveled. Since the GPS technology is rather noisy, we cannot assume to find an exact matching. To abstract the problem, assume we are given a polygonal curve alpha which represents Eric's path of GPS positions, and we are given a road map which we model as a geometric graph G embedded in the plane with straight line edges. We wish to find a path beta in the graph G which has the closest fauché distance to the GPS curve alpha. In our example, beta is highlighted in brown. The length of the black line segment in the lower right corner illustrates the optimal fauché distance, or in other words, the leash length. Also notice that the task we are solving is a partial matching task, which consists of finding a subpath beta in G together with a schedule of the dog walking on alpha and the man walking on beta.
Schedule who move faster, who move slower, and when. You see the person is waiting for the dog is making several wiggles, but we are finding what
In Solar
is a map, what
2003,
is
we
the
presented
best
an
path
algorithm
that
for this problem.
fits.
The runtime of our algorithm is order n square log square n, where n denotes the maximum of the complexities of the graph and the curve. Observe that this is only one log factor slower than the computation of the fauché distance between two curves, although we solve a more complicated partial matching task. We will now show some examples that have been obtained with the implementation of our algorithm. In this example, the curve describes a loop which runs close to a cycle in the graph. Hence,
Just to make sure, Eric GPS location, Eric did this path. Notice there is some error because of the GPS, so the green path of Eric is not exactly on the map. There is some gaps of, depending, your GPS quality could be large, could be small. And the blue is a map that is given to you. Trail map, road map given to you. We want to find, we want to assume there is some
the black
error
line
where is
segments
it
show the
actually on
mapping
the
of
map.
points between the curve and the path. Notice that the man traverses the bottom edge twice. In degenerate cases, this can lead to traveling the same edge back and forth several times. Notice that this is not a violation of the monotonicity constraints in the definition of the fauché distance, because we select a path in the graph which contains the same edge several times. In this example, consider the two parallel vertical line segments of the blue graph.
So I like this example because you have on the map a dead end street that ends right here, while Eric's path, Eric's driving now direction, was somewhere here. If I just try to align every point on the green trail to the closest point on the blue one, I'll just assume that Eric was driving along this dead-end street, and I could not continue over there. While you see that the green does continue. The fresher requires that the overall matching takes the whole spatial continuity into account. I find it a path on the map that I can continue.
Although the green curve is closer to the right segment, the man clearly prefers the left segment over the right segment because it allows a continuous schedule with a smaller leash length. This shows the advantage of using the Frechet distance.
Had I asked what is the Frechet distance between the blue curve and the green curve, if Eric we were trying to hypothesize that Eric is going in this way while Eric was in this way, then I need a leash that is connecting this point to this point, a very, very long leash. While if we let's hypothesize that actually Eric drives along this part, then the length of the leash is much shorter, meaning the Frechet distance is much shorter.
Like the Hausdorff distance, which are based on a local notion of similarity. A sketch of the algorithm.
Okay.
We use the notion of the free space
That's
diagram
more than you
for
need to
curves
know.
alpha and beta, which is defined for a given parameter epsilon.
It's
the free
just
space
a moment
consists
or
of all
two, so
pairs
let's
of
see.
points, one on alpha and one on beta, whose distance is at most epsilon. In the
Essentially, I'll put alpha on the bottom, kind of stretch alpha, making a straight line. I'll put the other curve beta on the y-axis, and now I paint every point as a white. I have some target idea about the length of the leash. Leash of distance 1. Can I do the whole trip with the leash of the distance 1 or not? If I can do the whole trip on the leash of distance 1, then maybe I can do it with even shorter leash. Then the next time if I tried 1 meter and it works, I'll try half a meter in the next iteration. If with 1 meter it's still too far away, then in the next iteration I'll try 2 meters instead of 1 meter, maybe then the distance. Then I can do the whole trip. Anyhow, given this one target distance, one target size in mind, I will paint every point. Remember, a point here corresponds to one location of the man, one location of the dog, one location on alpha, one location of beta, corresponds to one point over here. If it's white, then the distance is less than 1 meter, my target distance. If it's black, the distance is larger than the 1 meter distance. Now, after I painted this whole, what we call free space diagram, how do we know if there is a schedule of the person and the dog from the beginning to the end? Where is the beginning of the two curves? Beginning of alpha and the beginning of beta will be the lower left corner. The end point of alpha and beta will be the top right corner. Moving in the free space horizontally, only horizontally, if I move horizontally, what does it mean? That I'm moving on alpha but stays still in beta. If I moved horizontally, it means I moved on alpha, but the man moved, but the dog stays still. If I move vertically here, it means the man stayed still, but the dog was moving. If I'm moving in some diagonal, then they are both moving. If it's 45 degrees, then they are moving in exactly the same speed. What am I looking for after building the free space diagram is asking either any path in the free space that starts here and ends here. Start at the bottom left, ends at the top right.
On the right, the axes correspond to the parametrizations of the curves, and the white points correspond to points in the free space. Then the Frechet distance of alpha and beta is at most epsilon if and only if there is a monotone path in the free space which starts in the lower left corner and ends in the upper right corner. Observe that the monotone path encodes reparametrizations of alpha and beta. In our application, we consider the free space diagrams between an edge of the graph and the whole curve alpha, and then we glue these free space diagrams together according to the adjacency information in the graph G. We call the resulting structure the free space surface of alpha and G. Our task is now to find a monotone path in the free space surface. This monotone path has to start in some lower left corner and to end in some upper right corner of some individual free space diagram.
Okay. That's more complicated but still very similar to what we are going to describe in the Frechet coming up very soon, and very similar to the dynamic time warping. Dynamic time warping is not the Frechet, but it's quite related. So what is a dynamic time warping? Just checking the OBS. Dynamic time warping, DTW. Why time warping? Because it's like you are warping the time, like making the time on some, allowing the time to move very slowly sometimes or very fast sometimes. But so it's very talking about branding your algorithm. People will remember, I think, that it's brilliant to call your algorithm dynamic time warping. Again, I have a polygonal path P and another polygonal path Q. For simplicity, both of them have the same number of vertices. It doesn't have to be, but just to keep one letter less. Both of length n. And I'll assume here that we're talking about the discrete case. Both of the day Frechet and about the discrete case of the dynamic time warping. Discrete means when I measure distances, I'll assume that the dog and the person are on vertices only. Only the vertices count here. Okay, I don't care very much about what happens between vertices. Continuous version that we don't discuss in the course assumes that every point of the segments counts, that they need to move continuously. Discrete, I'll assume that they are jumping one step at a time. Here is my notation. P is denoted P1, small p1, small p2, all the way up to Pn, a bit blurry. Pn is the last vertex of P. Q1 dot Qm are where the dog moves along the red path. And the person starts at P1 and has to end at Pn. The dogs start at Q1, has to end at Qn. That's given, we are measuring the whole time. What I'm describing is the whole algorithm that eventually will give me a number. That's a distance between them. The dynamic time warping is a distance between the curves. And it will also tell me which vertex matches which other vertex. To have a precise example, here is capital P, that's what the man is going to move on. Here is capital Q, that's what the dog is going to walk on. And the matching that I'm trying to find will mean if it's actually the same path, that which point in P matches which point of Q. If it actually refers to the same road in the map, then which point makes sense to match to which other point, or if it's the same signal or the same signature or the same behavior of a stock. One of the main usages of dynamic time warping is people used it to predict behavior of the stock market. They looked at stock, looked at the graph of the stock. Here is the behavior of the graph of the stock in the last 2 weeks. Let's go over the history. Did we find anything similar to it? And the stocks that behaved similar to it, what did it do next 2 weeks from now when people used it for predicting behavior? back to our two curves, P and Q, when I'm talking about the matching, I'd like to know that not only what is the length of the leash, but that probably a good alignment between them is that they both start at the first vertex. That will be Q1. Then the dog will jump to Q2. The man will jump to P2, the next vertex. And now the dog, at this moment, the dog will take a break, doesn't move at all, while the man jumps to the next vertex, to the next vertex, to the next vertex. So all this cluster of vertices of P matches a single cluster of Q, a single vertex of Q. Again, a lot of the vertices of P will match a single vertex of Q. Then they'll continue along their way, jump to here, and now all this set of vertices of Q will match this vertex. What will it be? Maybe P30, the next vertex of P. How would I know it? Because the person will wait here when I find the optimal schedule. When I found the optimal schedule, they both started here. They both jump to the next vertex. Now the dogs doesn't move while the man keeps moving to the next vertex, next vertex, next vertex, until at some point they both move to the next vertices similarly. And now the person is the one that moves while the dog is running forward, matching many points. Okay, so that's a type of matching, type of alignment that I want to find. I want to find what is a good schedule. That's probably not a good schedule because, as you saw, the dog was running much, much further away, which means that length-ish, the man and the dog were very far away from each other. And again, in this animation, this is a bad scheduling. This is definitely not the optimal scheduling because the dog runs way, way further away. We are looking for a schedule that allows me to use a leash that is much shorter. So what is the rule of the game? The person starts at P1 and will end the trip at Pn. The dog starts at Q1, the first vertex of Q, and will end at Qa, the last vertex of Q. Now, we are thinking about discrete set of events. It's not a continuous motion, it's a set of steps. What do we have to decide? At each step, there are one of three options. Either the person jumps from one vertex to the next vertex, but the dog doesn't move at one particular step. Again, the person moved, say, from P1 to P2, the dog stays at Q1. An example. Other type of event is that the dog jumps from one vertex to the next vertex. Neither of them can jump over a vertex. Neither of them can move backward. Their options are either move to the next vertex or stay where you are. The dog jumps to the next vertex while the man stays where they are. The other option for one time step, they both jump from one vertex to the next vertex, both at the same time. So if we are back in this example, then they both start at P1 and Q1. Next, they both jump together to the next vertex, Q2 and P2. Then the dog stays for quite a while over here while the man jumps to the next. The dog doesn't move. At some point, they'll jump to the next vertices, jump together, and then the man will stay still. The dog will move next vertex, and then they'll do one more step. Okay. Now, I'm talking about matching and measurements and distance, but what am I actually measuring? Frasher will measure the maximum length of the leash that I need. Dynamic time warping measures not the maximum length of the leash, but every time that they step on vertices, I measure the length of the leash between them. How far away are the person from the dog? at this particular step, and I sum up the length of all the leashes. I sum up the length of all the timestamps, the total length of all the leashes for all the timestamps. How many timestamps do I need? It's not an exact answer, but I need a range. Well, how many timestamps do I need? P has n vertices, Q has n vertices. How many timestamps do I need until they are done? I don't know the exact answer, but I need a range. It's between something and something. Give me a scenario at which they need the fewest timestamps. Give me a scenario at which they need as few timestamps as possible. Again, P has n vertices, Q has n vertices. They move together all the time. And then I need n or n minus 1 timestamps. That's the fewest number. Minimum n timestamps. What's the maximum number? 2 times. Maybe the dog waits here while the person moves all the way to the next vertex. I spend n timestamps, and then the person moves. The person is finally at the end. Remember, he's not allowed to move backward, and the dog will move forward in another n timestamp. So we need somewhere between n and 2 timestamps. Now you see that there are different scheduling, but one schedule will be the person stays in P1, the dog will run all the way to Q1, to Qn, sorry, the dog will run all the way to the end, and then the person will start moving. That's one possible schedule. Another schedule is that they are moving together. But there is exponentially many other schedules. Each one of them can start, stop, whenever they want. What is the dynamic time warping is the sum of the lengths of leashes under the smallest, under the best scheduling. We will have to find an algorithm that will find. What we are going to do is to find an algorithm that will tell us what is the scheduling that leads to a penalty that is as small as possible. Penalty is the sum of lengths of the leashes. Again, every time that they stop, I measure the length of the leash. I take a centimeter, I take a ruler and says between this, if you're telling me that the dog was at Q2 when the person was at P17, I measure the distance between P17 minus Q2 to make sure that everybody knows distance. It would be P17 x of P17 minus x of Q2, the x coordinate of this point, the x coordinate of this point, this distance squared plus y of P17 minus y, the y coordinate of Q2, all of it squared, and help Pythagoras. This number is the length of the leash right here that we are using, just Pythagoras. Right? This is the length of this is this square plus this square root of what? Of the sum. Pythagoras. And we are summing up the length of all the distances. We will find out which schedule leads to the best total length of the leash. And this best length of the leash will also tell us what is the important word, what is the alignment for the matching. It is not a one-to-one matching, it could be multiple to one matching, but every vertex of P matches at least one vertex of Q. So I spent so far almost 50 minutes, and I still didn't tell you what the algorithm just represents the problem. So definition of the distance between two are so why are we using this definition? Because two trajectories might be very similar to each other, but the vertices are far away from each other. But that's a problem with the GPS. Where did we exactly did we sample? One moved faster. Around here, this trajectory, when we recorded it, this car moved very slow. It was a traffic jam, a lot of GPS points. When I was driving again around the same route, these routes are actually the same, but I moved much faster, so I got just one sample point. Okay, and you see a lot of partial list of where dynamic time warping is used. And Google for it, don't take my word, you'll see. See how many, other applications of dynamic time warping. Okay, let's start to, now we want to start paving our way toward an algorithm. When I had a string, when I talked about the LCS, and I had a string x equal a, b, c, f, and I denoted x of 1 dot dot 3, what did it mean? It was the prefix of the first three letters of x. In case of the LCS, longest common subsequence, already listed, x from 1 dot dot 3 meant takes the first three letters of x. Okay, and similarly for y. I'm going to abuse or use the same notation. Now I'm talking not about strings, but on polygonal curves. Here is a polygonal curves, P1, P2, P3, P4, P5, P6. This is a polygonal curve P. And you can all guess what do I mean by P of 1 dot dot 4. It's a polygonal curve, polygonal path that consists of the first 4 vertices of P. So P from 1 dot dot J is a polygonal path defined by P1, P2, dot, dot, dot. But when do I stop here? I stop at vertex Pj. This is a polygonal path that defines by the first j vertices. Exactly like the string. So, what is P of 1 dot dot 4? It's a polygonal path that consists of P1 goes to P2, goes to P3, goes to P4, and that's it. That's my polygonal path. This notation. Completely analogous to what we used in the LCS and what we used in the edit distance. So you know now what is P of 1 dot dot I. The first I vertices of the path P. Q of 1 dot dot j is the first Q vertices of the curve Q. What did we use C of ij in the case of the LCS? In the case of the LCS, if I have x, which was A, B, C, D, and y, which was C and B and F, then C of 3, 2 was what? The length of the LCS, the length of the longest common subsequent of x 1 dot dot 3, the prefix of the first 3 letters of x, and y from 1 dot dot 2. That was the length of the LTS. How many letters was I able to match? So in this case, it was to match the prefix of the first 3 letters of x, this 3 that comes here, to the first 2 letters of y, the C and B. And by the way, what is the answer for C3, 2 in the LCS? 1. Right. I have CB versus AB. I have CBF versus, I have ABC. What's going to be? ABC on X versus CB in Y. So I can match either the C to the C. I can match either the C to the C, or I can match the B to the B, but I have to pick one of the two. I cannot match both of them because they are not in the same order. One is not a subsequence of the other. They have to come in the same order. So that's what we used Cij for. What do I do now? I'm not in the LCS anymore, I'm in dynamic time warping. What will Cij denote? I'll use it completely analogously. I look at Cij for any 2 values I and j. Look at P, the first polygonal curve, look at the first I vertices of it. The prefix of the first I vertices of P, similarly the first j vertices of Q. Q from 1 all the way to j, compute the dynamic time warping. Dynamic time warping is a number, it's a sum of length of all the leashes you there. So Cij is the sum of length of all the leashes under the best schedule. The dog and man try to move so that the sum of length of leashes will be as small as possible. It's optimization problem. This notation, Pi minus Qj with double bars on the side is the Euclidean distance between Pi and Qj. The Euclidean distance, what we had on this scary formula earlier. People on Zoom, you're okay with us so far? Okay, let's try to make some statements. What is C1, 1? I'm looking at the polygonal path from P of 1 dot dot 1, the first 1 vertex of P. It's a polygonal path that consists of a single vertex, only P1. Similar, and the man needs to go on this polygonal path, but the man starts at P1 and ends its walking at P1 as well. It's also the last station. Similarly for Q, the dog starts and ends at Q1. So what is C11? So let's use this example of P. Here is Q. What the rule of the games? They started, the man and dog start they start measuring the distance, the length of the leash under the optimum scheduling when they start. Let's use green. If I'm doing something else here, let me. Green is leash. So I'm measuring the total sum of length of leashes when they both start at P1 and Q1. That is, I measure the distance over here. I need to pay this leash no matter what. That's the leash at the beginning. That's also the leash at the end. It's the only leash that I'm ever going to use in the case of C11. So what is C11? It's just the length of the leash, the distance between P1 and Q1. Next, what will be help me understand what is C12. I first need to understand what are the relevant pieces of the polygonal path. What is the polygonal path that I'm using out of P? P has a lot of vertices, but if I wrote one here, it means you're only looking at the prefix of the first one vertex of P. That is, we are looking at some trip of the dog, person and the dog, but the person starts at 1 and ends at P1. What's the dog, what is part of the path of the dog are we looking at Q? There is 2 over here, so we start at P at Q1 and at Q2. What are the leashes that we are going to use? What's the best schedule for the dog and the person? Well, the person cannot move. The person is stuck at P1. That's the meaning of writing the 1 over here. What could the dog do? One of them at each step must move, and the person cannot move, so the dog will start at Q1, and the person will jump, and the dog will jump from Q1 to Q2. What is the dynamic? What is C of 1, 2? It's the length of this leash plus the length of this leash. So C12 is the distance between P1 and Q1 plus the distance between P1, again, the person only, and P1, P4, person if you wish, minus Q2, the length of these two leashes. What is therefore C1, 3? It will be this, exactly the same thing. Okay, this quote just means what you have written above. So this is exactly P1 minus Q1 plus P1 minus Q2. Remember, now I wrote 3 here, so there is one more vertex. So plus P1 minus Q3. So I took the previous expression. And I added this distance, this length of 1 longer leash. We are just in the initialization of a table that will, again, very similar to the table that we use in the edit distance in the LCS. So what is therefore C1, J? It is C1, J minus 1. The sum of leashes that I had one vertex ago, like in the case of J equals 3, I took the sum of leashes that I had for J minus 1, so it's 2, some two vertices, and add to this number P1 minus Qj, the distance between the man and the dog at the endpoint. Okay, if that confuses you, then just write down the sum of all the expressions, P1 minus Q1, P1 minus Q2, P1 minus Q3, all the way up to P1 minus Qj. But notice a J over here. We are looking at the prefix of J part. And similarly, now we switch the rules. Now the dog is stuck at Q1. This dog cannot move. What is Ci, comma 1? It's just Ci minus 1, comma 1, plus the distance between the dog is stuck at Q1, Pi. The distance between the dog at Q1 and the person at Pi. That is the sum of all the leashes that looks like dog stuck at Q1 and the person jumps to the next vertices, and we are just summing up all these lengths. That's the init. Everybody's cool so far? I'm going to build an array. Again, assuming that you understood LCS and edit distance. I'm going to fill a two-dimensional array using dynamic programming where each moment I'm going to create a two-dimensional array C, where I'll be done, then C, I, and J, this cell C, I, J. When I'm done, we'll have to contain the best dynamic time warping between P1 till Pi and Q1 till Qj. So this cell, when I'm done, should contain, from here, when I'm done, this cell will contain the dynamic time warping between P of 1 dot I, Q of 1 dot J. It's exactly what is written in the first line on the what is written in the first line of the slide, except that now it is seen as a two-dimensional table. What did I do by this init part? I computed the values of the first row of C and computed the values of the first column of C. Okay. Now stay awake. We are getting to the punchline of the algorithm. I'm speaking of this algorithm for an hour and a half by now, but it's going to be an extremely short algorithm. So, assuming that at some point the person is at Pi and the dog is at Qj, we get to a point where the person is at P3, the dog is at Q3. Let's assume that there is such a moment. I'm not sure that in the optimal scheduling there will be any such moment. I'm not sure that when the person is at Pi, the dog actually will be in Qj under the optimal schedule, but for the moment, let's assume that yes. Because what I'm going to do is to actually check all possibilities of Pi and Qj, and one of them must be true. What is similar to computing the shortest path in a graph? I don't know if the shortest path from S to T, I don't know if the shortest path will actually go through Vi, but if it will go through Vi, then the path, which path will I go from S to Vi? The shortest path. I want to go to T, but if my path will happen to go through Vi, then I'll use the shortest path to go to Vi, obviously, as part of my whole shortest path. So idea here, I don't know that the dog and the man will be at this particular I and j, but let's assume that yes. So at some point the person is at P3, the dog is at Q3. Let's assume that yes, there is such a case and it's part of the optimum. So somehow there is some schedule that caused each one of them to move at its own time and brought them to the case of P3 and Q3. What do we have to pay in general? We will have to pay the length of the leash between P3 and Q3 as a last step, if that's part of the optimum. Can you tell me what was the schedule? What happened one step ago? What happened one time step ago? I'm not sure. What happened one time step ago? Now they're at P3, Q3. What happened one step ago? Either the person was one vertex earlier at P2, and the dog was still at Q3. Or that the person was already at P3, and in the last step, the dog was the one that moved. Or one step ago, they were at P2 and Q2, and both of them jumped. There are the only three options. One step ago, if now they're at PI and QI, then one step ago, in the last step, the dog was the one that jumped. So the last step ago, so that should be QI minus 1. So that should be QI minus 1. So in the last step, both the man and the dog jump. They jumped from, the person jumped from PI minus 1 to PI, the dog jumped from QI minus 1 to QI. So QJ. Or, what's the other option? The person was the one that jumped from PI minus 1 to PI, but the dog was already at QJ one step ago. Or the other option is that the person was already at PI and the dog was the one that jumped from QJ minus 1 to QJ. These are the only three options. Fantastic. So there was some let's assume that the first case happens. So let's assume that the first case happens. They both jumped. Let's assume that both jumped. So what is therefore the dynamic time hopping that I need to compute? What is Cij in this case, if they both jump? Cij should be Pi minus Qj. I need to pay for the length of the leash right now. But here comes the punch point. What is the optimum scheduling that brings them from P1 Q1 all the way to Pi minus 1 Qi minus 1? I have it computed already. What will be the optimum scheduling that brings them? What I'm looking for, what is the optimum scheduling that brings them from P1 Q1 to P2 Q2? And I have a number for it. In this case, I need to add to this number Ci minus 1, J minus 1. So Cij is definitely, I need to pay the leash, the length of the leash between Pi and Qj. No matter what, if they ended at I and j, if indeed they ended at Pi and Qj, then I need to pay the length of the leash between them right now. But what do I need to add to it? I need to add to it, in the case that they both jump, the optimum scheduling is the optimum scheduling, the minimum sum of lengths of the leashes, is already computed. Indeed, it will be C of I minus 1, J minus 1. Recursively, I already computed it. It's a smaller problem. But that's only in the case that they both jump. What if in the last step, before they are in PIQJ, the person in the last step, the person is the one that jumped from PI minus 1 to PI, but the dog was already at QJ. Then there is some length of leashes that involve the history, and there is optimum length of leashes that involves the history, but I already know what is the optimum for this problem. If you want, Ci minus 1j is the optimum length of leashes, the minimum distance, for which you start at P1, Q1 and end at Pi minus 1 and at Qj. That's just a definition of Ci minus 1j. It's very clever. Similarly, in the third case, and remember I still don't know which of these three cases happens. In the third case, the person was already at Pi minus 1 and the dog in the last step jumped from Qj minus 1 to Qj in the last step. What is the optimum scheduling that leads to this case? That leads us from, I'll write just the last case, that leads us to the case where the person was the one that jumped from P2 to Q to P3, and the dog was already at Q3, in the case of 3, 3. There are a few more leashes that you don't see, but their total sum optimally is written as Ci minus 1, J minus 1. Now, how can I decide what's actually happened in the last step? I don't, well, it's an open, they can do whatever they want, but they want the total sum of leashes to be as small as possible. If Cij assumes that I don't care about the future, I don't care about what happened after the INJ. They end at INJ. The last moment they are at INJ. What would be the last step? The both jump, or just a man jump, or just a dog jump? Wherever Cij is just, I'll take one out of these three options, I'll take the one that gives me the smallest weight. I want to pay as little leash as possible. So Cij, after all this long explanation, is the length of the current leash between Pi and Qj, plus the minimum of these three values. The minimum of these three values. The one that did is the best. The history doesn't matter. It's a cut and paste lemma that we saw for the shortest path. Once again, if my sub-problem is to bring the dog to Q3 while bring the person to P2, find the optimum scheduling that brings me to this location. And doesn't matter that this is just a sub-problem of a larger problem because there are more vertices to come. I'm sure that this problem will be solved optimally. Every sub-problem will be solved optimally. Everybody understand why Cij is just the length of the current leash plus the minimum of the three possible options. One of the three steps happens one step ago. That's the only options. What does it mean when I need to compute the value at this cell, at the INJ? Which cells do I need to read? I need to know what is Ci minus 1, J minus 1. But how am I going to write this table? See, I'm going to do raster scan. Start from I equal 1, fill all the cells. I equal 2, I equal 3. One row after the other. So when in particular, when I need to compute what is Cij, I need to use a value in the table. Ci minus 1, J minus 1. Where is this in the table? Which cell is this? if this is ij, I minus 1, j minus 1 will be the cell just diagonally from it. ij minus 1 is a cell just to the left. I minus 1j is a cell just above. So I need these three green cells to be computed so that I can compute the value at this red cell. Long speech. Let's see the algorithm. The algorithm is compute, do the initialization. We had the initialization of C. Initialization means what do you write on the bottom column? Sorry, what do you write on the left? Where's my stick? Initialization was compute all the values of the left column, compute all the values at the top row. That was the initialization. It's not on this slide. You had this look earlier. Now I need to compute the value of the cell, to compute what do I write in the cell, in every other cell. For I goes from 2 to n, for j equals from 2 to n, Cij is, it's just a theorem from the previous step. The theorem from the previous step is exactly what I write as the code of this algorithm. Cij is the distance between pi and qj, plus the minimum of these three values. Look at the minimum at these three values. Look at the smallest one, add to it pi minus qj, and that's what you write in the red. That's it. And what do I return to the user at the end? What is the smallest optimum length of leashes? CNN. It's a prefix, but it's a prefix that contains all of P, all the polygonal path P, all the polygonal path Q. What I'll give to the user at the end is a number that is written right here. And n square time, n square space. Not much problem about it. Now, that's just give me the total sum of lengths of the leashes. What happens if I actually want to find what is the leashes on the optimum scheduling? What did we do in the LCS? What did we do in the shortest path problem? We first computed the minimum or the optimum value as a number, the optimum cost, and then we paved our way in the graph. By the way, we asked how come there is a value here, some of the cells around it gave it its value. How come there is this value here? I can go trace back my way, going through the history, find exactly which I and j, which sequence leads me from this one to this one under the optimum schedule. So you first compute all these values, compute this matrix, and then you are looking at it backward. If you are not sure what I'm talking about, check what we did in the case of edit distance and LCS. Exactly the same process will allow us to recover what is CIIQ. This requires n square memory. If I just want to compute what is C and n, I talked about this trick yesterday, but I don't insist on knowing what exactly is the matching, just to ask, is the distance from this curve to this curve is smaller or larger than the distance between this query curve and a different one, just the number. I want to compute this value, and I want to only use linear space instead of n squared space. What was the trick that we discussed yesterday? I read from one row, I read values from one row, and I write values into another row, into the next row. But once I'm done writing values into the second row, I don't need the first row anymore, so I can start writing into the third row. It was this choreography that consists like this one. You just need two rows at each moment, the row I and row I plus 1. But when you're done writing into the second row, then you don't need the first row anymore, so you can use this array to write into it. Okay, let's start to talk about pressure. We have 5 minutes, let's talk about pressure. Again, dynamic time hopping. So again, dog and person measurements. Again, sequence of steps. The dog is allowed to move forward. The person is allowed to move forward. There is a leash involved. But dynamic time warping sum up the length of the leashes throughout the whole path. Dynamic time warping sum up total length of the leashes. So if this is one curve with many, many vertices, and this is very similar curve except for one curve, there's only one curve, but billion vertices are here and billion vertices here, then the dynamic time warping between them will be quite small. But the dynamic time warping between them, the sum of lengths of leashes, is quite small because there is only one outlier. And if that's what you want, that's fine. But if you want to ask what is I want to say all the points of P matches all the points of Q is small distance, then I don't care about the sum of lengths of leashes. I ask what is the longest leash or what is the shortest leash that I can still use. That is, right now I'm asking what is the shortest leash for which I can do the whole trip from P1, Q1 to P and Q. And there is a very important trick that I want to show you, useful here, useful for many other algorithms. I will not try to find the best leash ahead of time. I first build an oracle that takes P and takes Q, but also takes some number R that you have in mind, 1 meter. R is the length of a leash that you have in mind. Start from 1 meter. And what will the Frechet algorithm return for you? The Frechet will return yes or no. You can make the whole trip from P1, Q1 to P and Qn. Again, different scheduling. Each one can jump or move forward whenever they want. But you can make the whole trip and never use a leash of more than R. So we want to say at every instant they stop, we measure distance between the person and the dog, length of the leash. And we'll say that the Frechet returns a Boolean answer, yes or no. If the code returns yes, then leash of length R will do for you. And then you will try a shorter leash, maybe a leash of half the size. If the Frechet says no, it's because there are 2 points that no matter which schedule I'll use, I cannot use a leash of this length because there are 2 points that are too far away, no matter what is scheduling, and then the Frechet will say no. Make sense? So the input is, and it's, I don't know why, but it's really confusing for students earlier. It takes P, it takes Q, and it takes now a number that you have in mind, the target length of the leash. And it will return use a shorter leash or use a longer leash. And then you're just doing binary search using this code until you actually find what is the optimum length of the leash. And in the homework, I'll ask you a few tweaks of how to do this binary search cleverly so that you're getting to the optimum length of the leash. That is the critical one, the minimum one that you can do the two. But is the Frechet problem clear to everybody? I'll state it once again. Takes P, Q, and a length of a leash, 1 meter. And there is again a series of steps. At every time step, either the dog jumps to the next vertex, or the man jumps to the next vertex, or they both jump to the next vertices correspondingly. Person, of course, only on P, dogs only on Q. And if there is any such scheduling, who moves when, for which the distance between the dog and the man is not more than R, then I'll tell you, you started at P1, Q1, they end at P and Qn, never use the leash of more than R, then the Frechet will tell you, yes, possible. If the R is too short, and no matter which schedule I used, no matter who jumps when, I cannot move them all the way till the end, the Frechet will say no. That's what I need this algorithm to do. Clear? And as we look at it, this algorithm is simpler, it's very similar, but simpler than the dynamic time mapping. But the confusing part is to understand what I need this algorithm to do and what the yes and no means. My experience with students, for whatever reason, is that it sounds very strange. This algorithm does not compute the optimal length of the leash, the shortest one. I will use it to compute the shortest length of the leash, but this algorithm by itself takes a length of the leash that you have in mind and will say not too short, not or long enough. One of the two options. Good. Continue tomorrow. Maybe we'll do a bit active learning or something. If you want, maybe some of the midterm questions or homework 7 or maybe, and you'll have soon a new paper, homework 5 will come soon. Thanks for everybody.
So our deadline